Okay, Assalamualaikum and good morning, everyone.
Good morning, sir.
Morning, sir.
Okay, so for today, we will continue with our lecture, with lecture 3C, and also we will do tutorial number 7. So lecture 3C is about time response of second order system. So last week, we have learned about the time response for first order system. And today, we will continue looking for the time response of second order system. Okay, so after completing this lecture, you guys will be able to determine the time response of second order system using poles and zeros. So I hope you still remember what are poles and zeros. And then determine the time response of second order system using damping ratio and natural frequency. And lastly, we will determine the performance parameters of second order system. So second order system, basically the general form of the transfer function GS is given here, B divided by S squared plus AS plus B. Okay, so the general equation for GS must be in this form. Okay, so also make sure that the input is unit step input. Okay, so for a second order system, there are 4 types of response. So the response depends on the poles, as I stated earlier. So the types of response are overdamped, underdamped, undamped, and critically damped. So I think you have seen these terms maybe during your matriculations or diploma. Okay. And all of this is time response can be determined by finding the poles of second order system. So let's look at the first time response, which is overdamp. So for example, you are given the transfer function GS 9 divided by S squared plus 9S plus 9. So we can find the poles by finding the value of S when the denominator equals 0. So you can use quadratic formula, okay? So when you use quadratic formula, you can get poles number 1 at negative 7.8 and poles number 2 is at negative 1.1. So there are two poles that are real, two real poles or two real roots of the denominator. And you can plot the poles on S-plane. So for poles, we use X or cross to represent poles. And the general solution for overdamped time response is given as this one, okay? And you can also plot the time response for this transfer function. Okay, so for overdamped time response, when your poles are, when you calculate your poles and you get two real and distinct poles, then your transfer function or your system is overdamped, okay? So for overdamped system, you have two real poles or two real roots. Now let's look at underdamped. So let's say you have transfer function GS equals 9 divided by S squared plus 2S plus 9. So you find poles using quadratic equation or quadratic formula. So you get two poles here. So here your poles has imaginary number. So imaginary number we represent by the letter J. Okay. So maybe in mathematics subject that you have taken, we use symbol I. Okay. But in this subject we use J. So why the difference? I don't know. For fun, kot. Okay. Saja nak bagi pening kepala. So J represent imaginary number, Okay, so some student, they don't know what is imaginary number. So imaginary number equals j equals square root minus 1. Okay. Okay, so ada student dia tanya, sir, kenapa j squared equals minus 1? Tak faham juga, boleh masuk form 1 balik. And then you can plot the poles on S-plane. Okay, so notice that in S-plane, both of the poles have the same real values. Okay, so real values is at minus 1, but different in complex value or the imaginary axis value, which is j square root 8 and negative j square root 8. Okay, the difference is positive and negative only. Okay, so please aware this later in next lecture, maybe in 2 weeks time. You will notice the reason of this difference and the importance. Okay, and the general solution is given by this equation. And if you plot the time response dia macam ni. Okay, so for a system to be under them, your poles must have imaginary values. Now let's look at undamp. So let's say GS equals 9 divided by S squared plus 9. So we find the poles. So we get 2 poles, but without the real parts. Okay, so imaginary poles, but without the real parts. So if you plot in S-plane, so the real part is 0 at the origin. And the general solution is this. And if you look at the time response, so the system will keep oscillating without showing any sign of stopping or reaching a steady state value. So the difference between undamped with the previous two types of time response is that the time response oscillate, but after some time it will reach some one steady state value. Okay, similar with this one, so it will reach a steady state value. But for undamped system, it will keep oscillate until infinity. Okay, and it doesn't reach a steady state value. So that's why the name undamped. Undamped means tidak apa tak bahasa Melayu dia, lupa dah bahasa Melayu dia. Tidak terdamp. Okay, so for undamped system, you must have two imaginary roots, but without the real parts. So lastly is the critically damped time response. Okay, so let's say GS equals 9 divided by S squared plus 6S plus 9. So we find poles. So we get only one poles for both of sigma 1 and sigma 2. So we get two poles but equal in values, okay, and real. And if we plot in S-plane, so both of the poles are exactly on the same real axis, okay. So dia plot macam tak sama lah, sebenarnya sama, dia nak tunjuk dia dua. Okay, so the general solution is this one. And if you plot the time response, it's this shape, okay. So for critically damped, your poles will be two poles but equal in value and real values, okay. Okay, so let's summarize a bit about the four different types of second order system. So if your poles are real and distinct, then it is an overdamped system. Okay, and if your system has poles that are real and imaginary, so it's an underdamped. So for undamped, if your poles are imaginary only, okay, so it will keep oscillate. And lastly, critically damped, if your poles are real and equal in values or repeated. Okay. Okay, so why we need to know about the different types of second order system? Because later in the following lectures, actually we will assume system of order 3 and above, like third order system, fourth order system, and so on. We tend to assume it to have properties similar to second order system because it also have oscillation, okay, like undamped, underdamped, critically damped, and overdamped. So it's difficult to analyze like third order system, fourth order system by finding the poles and also plot the time response. Okay, we usually make it similar to second order system, but we excluded this kind of analysis in this subject because it's too abstract. Okay, macam matematik sangat. Kang kata salah kos pula. Okay, so let's look at describing second order system using natural frequency and damping ratio. Okay, so I hope you guys can follow what I explained just now because I think it's kind of straightforward. Okay, not many theories. Okay, benda-benda hafal je. Okay, boleh buat toyo lah. Lagipun online. Okay, tak payah toyo. Okay, so a second order system can be characterized by using natural frequency and damping ratio. So what is natural frequency? Okay, dalam bahasa Melayu dia frekuensi asli. Mungkin dulu pernah dengar. So natural frequency we represent by the symbol omega n, and damping ratio is represented by this apa tak nama dia? I think it's tak tahu. Okay. Okay, I call this damping ratio. 3 terbalik. Tapi ni macam ketiga, tak tahu benda. Okay, so let's look at natural frequency first. So natural frequency of a second order system is the frequency of oscillation of the system when the system having no damping, okay, or without damping. So for a system to have no damping, we first assume the center terms on the denominator here as 0, okay. So first we assume this part as 0. And then we find the poles on GS. So when we find the pole, then S will equals plus minus J square root B. And the square root B here is our natural frequency, okay? So square root B is the natural frequency. So it's the value of frequency when the system oscillate without damping, okay? Maksudnya dia oscillate tanpa henti, okay? So therefore, omega n equals square root B, or B equals omega n squared. Now, what is damping ratio? So from the general equation just now, damping ratio equals damping ratio equals A over 2 times omega n. Okay, so this formula mesti memorize. Okay. Tak ada definition yang mudah difahami. Okay. So we can substitute back value of A and B from natural frequency and damping ratio into the general equation for second order system. Okay, we substitute back, and the new general form of second order system is shown here. Okay, so this is form number 1, and this one is form number 2. Okay, so we have two form. Okay, so we can describe our second order transfer function as b divided by s squared plus as plus b, or omega n squared divided by s squared plus 2 times damping ratio omega n s plus omega n squared. Okay, so there are two general form equation or transfer function for second order system. So we can use damping ratio to determine the type of second order system. So just now we have 4 types: overdamp, underdamp, undamp, and critically damped. But now we can use damping ratio. Instead of using poles, we can use damping ratio to determine the types of time response. So if your damping ratio is bigger than 1, then the system is overdamped. If damping ratio equals 1, then the system is critically damped. If the damping ratio is in between 0 until 1, then the system is underdamped. And if the damping ratio equals 0, the system is undamped. Okay, jangan tanya what happen if damping ratio is negative. Okay, tak tahu. Tak ada. Okay, hanya ada 4 jenis. Okay. So this one is kena ingatlah. Okay. Semua benda pun kena hafal. Apa je yang tak hafal? Okay. So let's look at tak ada example. Okay. Later on we will see some tutorial on how to find damping ratio and determine the nature of the time response. Okay, so similar to first order system, there are certain characteristics or performance of the system or second order system. And usually we are focusing only on underdamped oscillation. The reason is because underdamped oscillation is something that I think desired, okay, or easily achieved when designing a control system. When you design a control system later on, you are usually wanting the system to be stable. Okay? So a stable system usually can be achieved easily by making it underdamped. Okay. So for performance of second order system, we are going to look at determining the performance only on underdamped oscillation. So underdamped oscillation usually will have this kind of overdamped, okay? Underdamped. Underdamped oscillation will have this kind of graph, okay, or time response. So the maximum value here, we call it C max. The steady state value, or when the system reach a constant value, we call it C final. And the other things like 1.02 C final, 0.98 C final are 2% difference between 2% difference from the C final. And we also have 0.9 C final and 0.1 C final. Okay, so the most important thing that you need to know is where is the C max and also the C final. Okay. Okay, so for underdamped, you must have the damping ratio between 0 and 1. Okay, so when your damping ratio is between 0 and 1, then the system is underdamped. So there are 4 performance parameters for second order system underdamped. Okay, so first one is rise time, second is peak time, third is percent overshoot, and lastly settling time. Okay, so these 4 parameters, we will use this again in lecture chapter 5. Okay, we will use this again. So I want you to from now understand how to find this from maybe from graph or from formulas. Okay, so let's look at these performance parameters one by one. Okay, so firstly is the rise time. So rise time is the time required for the waveform to go from 0.1 of the final value to 0.9 of the final value. So I think this is similar to the first order system rise time. Okay. So there is no precise relationship to be used in second order system. So compared to rise time in first order system, we have an equation given or derived. But for second order system, there is no precise analytical relationship. So you must use graph. So this is an example of graph of rise time times natural frequency or natural frequency times rise time against damping ratio. So there's a plot given. So you can populate populate the table. Okay. So the second performance parameter is peak time. So peak time is the time required to reach the first maximum peak. Okay, so it's the time required to reach the maximum values. Okay, the first maximum values. So the formula is Tp or the peak time equals pi divided by omega n times square root of 1 minus damping ratio squared. So from the graph, it's the value of time when the system reach Cmax here. Okay, it's Tp. Okay, Tp is the time when the system reach maximum value or Cmax. Formula ni, macam mana nak hafal, pandailah. Okay, sebabkan exam online, kita tak bagilah list formula. Pandai cari dalam nota. Dah ada dah circle. Okay, next one is percent overshoot. So percent overshoot is the amount that the waveform overshoots from steady state value. Ataupun kita tengok dari graph lah. So the formula is percent overshoot or percent OS equals 100 times epsilon or not epsilon, exponential of negative damping ratio pi divided by square root of minus 1 minus damping ratio squared. So from graph, dia adalah value, percent value different this one, okay? Okay, so you find the percentage difference between this Cmax and C final from your graph. So it's the value of the system when it overshoots, okay? Overshoot from its steady state value. So steady state value is at C final, but the system dia oscillate or dia bergerak lebih sebanyak Cmax, okay, from the C final values. So the percent overshoot is calculated by finding the percentage difference between Cmax and C final. So the formula is also given as percent OS equals Cmax minus C final divided by C final times 100. Okay, just finding the percentage difference. Okay, and lastly is the settling time. So the settling time is the time required for the transient damp oscillation to reach and stay within 2% of the steady state value. So the formula is Ts equals 4 divided by damping ratio times omega n. Okay, so settling time is when the time taken when the system is within these two lines here, 1.02 C final and 0.98 C final. Okay, so when the system is within this line, then the time taken to reach that particular response, a particular part of the graph is known as settling time. Okay, so we have 4 different performance parameter for under dam. Okay, under dam time response second order. Okay, so let's look at example. What are the example yang tak ada? So let's say you have GS equals 361 divided by S squared plus 16S plus 361. So find omega n, damping ratio, TS, TP, TR, percent overshoot. Okay, so firstly, we can find omega n and damping ratio by looking at the denominator. So omega n squared equals 361. So from the formula previously, okay? Okay, so let's write this down. Omega n squared to damping ratio omega n. Lupa dah formula. Ya, apa tadi? Omega n squared divided by S squared plus 2 damping ratio omega n plus omega n squared. Okay. So this is the general formula. So omega n squared equals 361. So square root, you get 19. And then you can find damping ratio. So damping ratio equals 0.421. And then TS, settling time, just use the formula 4 divided by damping ratio omega n. So you get 0.5. And TP, you use the formula, so you get 0.182. And percent overshoot. So you get, you just use the formula, okay? So you get 23.3%. And then to find TR, so you need to populate the graph. Okay. So dia dapat 0.079. So omega n, damping ratio is 0.421. So it's somewhere here. So find from the graph, you get about 1.5. So 1.5 equals TR times omega n. So omega n is given by 19, or you found already 19. So just bring it over to the right. So you get rise time 0.079. Okay, straightforward je soalan dia. Or interpolate. Okay, so that's the end of this lecture. Let's look at tutorial. Okay. Oi, tengah kelas ni. Tiba-tiba download. Betul. Dia pakai step input saja. Ada yang lain tapi maybe tak payah belajar lagi kot. Bukan belajar sekarang lah. Maybe tak penting kot. Entah. Tak pernah jumpa lagi. Sakit hati. Okay, so let's look at the question. Okay, so from tutorial 7. So tutorial 7, question number 1. Okay, sekejap. So question number 1, determine the damping ratio, natural frequency, and type of response of the following second order system. Okay, question A. Okay, so we go back with the formula, the general form formula. It's omega n squared divided by s squared plus 2 times damping ratio omega n s plus omega n squared. Okay, so the first one is omega n equals 400. So we get omega n squared equals 400. So omega n equals 20. And damping ratio. Tak ada calculator. So you get damping ratio equals 6/20. So 6/20, it's between 0 and 1. So the system is under damped. Okay, so we go back to the lecture. So between 0 and 1, it's under damped. Okay, so the system is under damped. Yeah. Okay, question B. So omega n squared is 900. Okay, so omega n will be square root of 900. So equals 30. Okay? And then damping ratio. So damping ratio or 2 times damping ratio omega n equals 90. Okay, so you just take the middle value. So damping ratio equals 45 divided by 30. 45/30. So you get a value equals 3/2, 1.5. So 1.5, it's bigger than 1. So the system is overdamped. Okay, senang je. Macam bukan subjek universiti. And then the third one, so omega n squared equals 225. 15, okay, should be 15. Can. And then the damping ratio. So the middle value is 30. So 2 times damping ratio omega n equals 30. So you get the damping ratio equals 1. Okay. So if you look at the classification just now, so when damping ratio equals 1, it's critically damped. And lastly, for question D, so natural frequency omega n, omega n squared equals 625. So square root 25, okay, 25. So the damping ratio, 2 times omega, 2 times damping ratio times omega n equals 0. So equals 0. So damping ratio is 0. So when damping ratio is 0, so system is undamped. Okay. Okay, fairly straightforward lah kalau soalan macam ni. Maknanya tak keluar final lah. Okay, so let's look at question number 2. Okay, figure below is a unit step response of a second order system. Okay, so this is a time response after a 4-second order system under unit step input. Okay. So question asks, approximate the damping ratio, natural frequency, rise time, settling time, percent overshoot, and peak time. Also determine poles and the transfer function. Banyak pula soalan. Okay, so for this kind of question, saya dah ada jawapan dia. Baik, tunjuk jawapan. Okay. So it's actually taken from slides from previous semester, okay? Previous lectures, previous semesters punya. Okay, so the same figure, same question, okay? So the most important things that you need to remember is where is C max and where is C final. Okay, so you need to determine where is C max and also where is C final. So from this graph, C max is somewhere maybe 0.45. And C final maybe somewhere here, okay? Okay. 0.34, 335, okay? Just approximate, okay? Okay, so the first thing that you need to do is to calculate the percent overshoot, because percent overshoot can be determined by using C max and C final. Okay, so you use the formula C max minus C final divided by C final times 100. Okay, so C max, I said just now, it's somewhere 0.45 or 0.44, wherever that you feel okay. So just approximate. And then the C final is 0.34. Okay, calculate using the formula to find percent overshoot. And then you find, when you find the percent overshoot, then you can use the formula for percent overshoot to find damping ratio. Okay, so you just rearrange damping ratio in terms of percent overshoot. So you get this formula here. damping ratio equals negative ln percent overshoot over 100 divided by square root of pi squared plus ln percent overshoot over 100 squared. Okay. Okay, so these two formula you will see it more in chapter 5. Okay. So for now, hafal or write in write a notes. Okay. And then use this formula and substitute percent overshoot using this calculation. And you'll get damping ratio equals 0.2. Now you have your damping ratio, then you can find the natural frequency omega n. So the formula, you can either use Ts or also Tp. But first, you need to determine Ts and Tp from the graph, okay? So the easiest time characteristics is T peak, okay? Peak time, because you just need to know where is the maximum value of the graph. So the maximum value is somewhere about maybe 1.1, okay, somewhere about here. Okay, 1.1 or 1.2, okay. So that's the easiest. If you want to know, if you want to use settling time, it will be slightly harder because you need to know where is 2%, okay, 2% from settling time. Okay, susah sikit. So the easiest one is finding the peak time. So when you find the peak time, so it's about 1.2 second. So substitute back into this equation. So you can get omega n. Okay, soalan ni jawapan ni dia daring sikit. Dia guna settling time. Dia tak nak guna peak time. Okay. But whichever method you use, I would suggest use peak time because it's easier to determine straight away from the graph. Okay. Settling time, siapa nak guna? Pandai-pandai lah. Okay, so here you get apa oh ni, okay, abaikan kesilapan di sini. Apalah buat nota ni. Whatever. Okay, siapa buat ni saya tahu. Kita highlight dulu. Okay, and if you use peak time, use this formula, you will get the natural frequency. Okay, so just substitute damping ratio and the peak time, you get natural frequency. So now you have damping ratio, natural frequency. So you can use that to find settling time. And then you can also use damping ratio and natural frequency to find the transfer function of GS. Just substitute back into the formula, the general formula. And then the question also asks for poles. So for poles, you just solve this denominator, find S when the value equals 0. And then the rise time. So the rise time, you need to use the table, okay? The table that given in the slide just now. Okay, so you just use this table and using a similar method as this one, okay? Tu je, okay, untuk soalan ni. Okay, and the question just ask, okay? Kalau macam hamda lecturer ni merepek, just tanya je. Okay, let's go to question number 3. So figure below shows the poles of an underdamped second order system. Determine the damping ratio, natural frequency, settling time, percent overshoot and peak time. Okay, so the question gives you poles. So let's write the poles first. Maybe you cannot, maybe you are confused from the graph. Let's write it in terms of equation for the poles. Okay, so poles S or sigma equals -3 plus minus J7. Okay. Okay, so real plus minus imaginary parts. Okay, so I think it's better to write this in word tadi lah. Mana word ini? Okay, so sigma equals -3 plus minus 7J. Okay, so this is the poles. So what you need to do is from the poles, you find the quadratic equation. Okay, so you can do this by writing something like this. Okay, sigma 1 equals -3 plus 7J. Sigma 2 equals -3 minus 7J. And then rearrange it to make it equal 0. So you get sigma 1 plus 3 minus 7J equals 0. Sigma 2 plus 3 plus 7J equals 0. Okay, multiply both of them and replace sigma with S. Okay. Ni masa SPM belajar. So S plus 3 minus 7J. S plus 3 plus 7J. So multiply, you get S squared plus 3S plus 7JS plus 3S plus 9 plus 21J minus 7JS minus 21J minus 49J squared. Okay, simplify. So this is can be cancelled, this cancel. Okay, so ni J squared becomes -1. So you get positive 49. So you get S squared plus 6S plus 49 plus 9 plus 58. Okay, harapnya betul lah. So the transfer function for the system GS equals 58 divided by S squared plus 6S plus 58. Okay. So dia tak nak pun transfer function, lebih-lebih pula jadi. And so now we look for the damping ratio and natural frequency. So natural frequency omega n squared equals 58. Okay, so omega n equals square root 58. So damping ratio okay, so you just rearrange, so you get damping ratio equals 3 over square root 58. Okay. So it's in between 0 and 1. So it's under damped. Okay, betul lah, under damped. And settling time, just now formula dia TS equals 4 over omega n, kau tak ingat dah. And percent overshoot, you just use the formula, okay? After you find omega n and damping ratio. Okay, so let's go back and look at the formula. So for the settling time, 4 over or damping ratio omega n, percent overshoot, this is the formula, and peak time, this is the formula. Okay, so when you find omega n and damping ratio, then to find the performance parameter, you can straightaway use the formula. Okay, so it's all about formula in this topic. Okay. Okay, so that's all for tutorial 7. Any question before we end this lecture?
Sir.
Yep.
Yang 3 bahagi square root 58 macam mana, sir?
Ni formula dia. We go back to transfer function tadi. Ni yang tengah ni 2 darab damping ratio omega n sama dengan 6. Susun-susun dapat 3 bagi square root 58. Okay.
Okay, sir.
Okay, ada question? Okay, so second order system we have covered today. So I hope you guys understand the basic concept, okay, for second order system, and you can also now start doing part 3 for project 1. Okay, so you can do part 3 because part 3 is about second order system. And then please also understand about this thing, the peak time, percent overshoot, and settling time, because we will see this again later in chapter 5. Okay, because we will use second order system, the performance, the performance of second order system to design a controller. So please understand, especially overshoot and peak time and settling time. And you can start doing the project part 3. And also, I think by the end of this week, quiz number 3 will be released. And I think submission time is end of next week, mid-semester break. So I hope you guys understand this topic. And after this, we will move on to lecture number 4 or chapter 4. And that's it for today's class. Thank you very much. Assalamualaikum and goodbye.
Thank you, sir.
Thank you, Dr.
Thank you, sir.
Thank you.